Okay, so we talked about the nearest neighbor concept. Let's talk about the instance space. To classify a new object, an unseen data record, we have a new object, we want to classify it. Just like we have the new flower, we want to classify it. We may compute the distance between the new object and each element in our instance space, which is our data set, and the nearest or k nearest neighbors of the object are located. The class of the object is then decided by the class of the k nearest neighbors, or the nearest neighbor. Right? So that's what we said here. So we said which one should we, what color should we classify the green as, red or blue? And we can classify it as red if we choose just the closest one, the nearest neighbor, or depending on the size of the neighborhood, we'll get different answers. Here we have a new instance which is like this thing over here, this thing, and we have, these are our kind of samples, and so we're trying to say what is this, and we say what is it closest to in our set of samples, and then we give it then we classify it. So we might classify it as an airplane. Okay, so we want to classify the new instance as one of the objects in the memory. I'm not sure why they call this box the memory, but anyway, we need some way to measure how close the new instance is to any of the given objects. So is it more similar to this? Is it more similar to this? It means how close is it to this? How close is it to that? It's not exactly the same. This is not exactly the same as this picture, and so on. So how close is it? We need some way to measure how close the new instance is from any of the given objects. We can consider different factors. That means different variables. For example, the weight, the color, the cost, maybe the orientation. This one is kind of slanted and this one isn't. Okay, whatever variables we think are important. Then we need some way to say how far away the new instance is from each given object with respect to each particular variable. So, like in terms of the weight, how close is this to this one? How close is this to this one? How close is this to this one? And then, so that's with respect to weight. Then talk about the cost. How close is this to this in cost? How close is this to this in cost? And so on. So with respect to each variable, we have to decide how close it is. When thinking about the weight variable, the meaning of distance is obvious, right? Because these are just numbers, so the distance is just the difference between the two numbers. Just the weight of the new instance minus the weight of the bus, for example. So weight, so the weight of this versus minus the weight of this would be the distance. But if we're talking about a variable of color, of course this doesn't have any color, they're all black and white, but if we had color, but if the variable is color, then what do we mean by distance? So we'll have to be a little bit more creative in this case to get at something that's useful in talking about the distance. What does it mean to be close when we're talking about color? So it really depends on how you're using this. Okay, next thing is called classification rules. So this is let's see, we did what before? Nearest neighbor. We were talking about instance space and classification. So now, going back to more generally classification and classification rules. Basically, a classification rule is just an if-then rule. So in the iris data set, it might be something like, if the stem width is less than 2, then it's an iris setosa. Or in the case of a loan application, it could be something like, if education is greater than 16 years and income is greater than $55,000, then we have a good candidate for a loan. Okay? Now we use some fancy words. Conjunctive description of features in the if part and a class outcome in the then part of the rule. So what does that mean? Conjunctive just means that you can do and. Like in the second case I said, if education is greater than 16 and income is greater. So you could do like a bunch of ands if you wanted. And then you have then, good candidate. Okay, so the if part can be conjunctive, can have a lot of ands in it. And the class outcome is in the then part. So remember here, the class outcome was Iris setosa, Iris virginica, and Iris something else. So that's the class outcome is here. And here, the class outcome is good candidate or not good candidate. So after the then part, or in the then part, comes the class outcome. How do I do this? Okay. Rules may also involve several values of variables. Such rules are known as rules involving relations or simply relations. For instance, the following rules may be discovered and used to distinguish whether an object is lying or standing. So like you take a picture of an object and then you want the computer to decide whether it's lying or standing. Maybe it's a person, I guess. So if width is greater than height, then lying. That's a rule. Maybe that's not true, but that's a rule. If height is greater than width, then standing. Or I should say maybe it's not always true. Okay, more with classification rules. Decision trees. So we've seen these kinds of decision trees before. So here we have age group rather, young, middle-aged, and senior. So this means that the age, remember we said that the nodes are the variables. So that means that the age variable apparently can take on one of three values: young, middle-aged, and senior. So it's not a numeric variable, it's a categorical variable. There's just three categories. Risky, I don't know what that is. I mean, I don't know what values it can take because there's no branches coming from here, or no links coming from here. Drive mileage, short or long, I don't even know what that means. And health, good and poor. Okay, so this is a classification tree, or a decision tree. And let's see. For example, if age group is middle-aged and drive mileage is long, then we classify this thing as, or person, as risky. Okay, so that's the way it works, whatever this means. So we have the internal nodes. This one, this one, this one, and this one are the internal nodes. The leaf nodes, these are the leaf nodes. The links connecting the nodes. Typically the leaf node will be a class label. So these are generally the class label, a possible value of the class variable. And by the way, that's also called a level of the variable in some other discussions. Okay, so the levels would be safe and risky. The level for age group would be risky, drive mileage, and, no, sorry, wrong. The level for age group would be young, middle-aged, and senior. Okay, now we have some other decision trees. Sometimes the variables are numbers, numeric. Some trees are so-called binary trees. So here we have age group now is kind of numeric, less than 20, between 20 and 59, and greater than or equal to 60. Okay? So that's numeric. Also drive mileage is kind of numeric. Some trees are so-called binary trees. Binary links are associated with a true-false outcome called Boolean. So Boolean means true-false. The tree on the right shows a binary tree version of the tree on the left. So here you can see that before we had, for age group, we had 3, but now we've broken it up into just binary choice. So then it can be called a binary tree because all of these are only binary. Traversing the tree from top to bottom results in a classification rule. We already saw that. Like you say, if age group is less than 20 is false, and age group is greater than 60 is true, and health is good, then safe, or something like that. No, that didn't make sense. But health is good, yeah, then safe. Okay. Okay, next thing is called estimation. Estimation is very similar to classification, except that the output of a continuous target variable is of interest. So before, we had something like the output variable was safe, risky, or iris, Setosa, iris virginica, and whatever the other one was. However, if the output variable is a continuous variable, then we call it estimation. The process of estimation is similar to that for classification, which also involves building an estimation model. So this could be called a model. These are both called models. And if we have a continuous target variable or output variable, we also want to build a model. The process of estimation is similar. Okay. And then using the model to estimate the value of the outcome variable. The output patterns, i.e. an estimation model, may take the form of a function, a theorem, or a network. For example, this one is a function where n represents the force pressed on the accelerator pedal. And f of n is what? The speed. Okay, so the harder you press on the accelerator, the faster you go, right? And this supposedly tells you the amount of, if n is the force that you press, this formula supposedly tells you how fast you're going to be going. Okay, this function, now how would you get such a function? How would you know that it's n squared plus 2n minus 10? Now, for every car, it's going to be different, right? If you press, a certain amount on one car's pedal, you're going to go one speed. If it's a different car, you'll probably go a different speed. So for every car, it would be different. And how do you know what this function would be? Well, you just have to test the car over and 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 over again. Okay, so you get lots and lots of data, and then you try to build the model. Okay. So it says this function is obtained by exhaustively testing the mappings between different speed values with corresponding n values. So it just means you're testing. When you press n, when you give n as the input, what's the speed? A different n, what's the speed? Different n, what's the speed? So looking for a relationship or a mapping between n and the speed. Most of the time, functions are approximate, so this isn't going to work exactly right. No precise mapping can be found from the arguments, n is the argument here, to the values, to the output values. And regression is clearly that kind of situation. Remember, we had a line that tried to fit the data, but it didn't fit the data perfectly. So it's not precise. It's approximate. So that was called a function. We also have things called theorems, which we can do, and we also have networks, like artificial neural networks. And actually, theorems and networks are actually just functions, but sometimes they will distinguish between them, but they're actually just functions. Okay, let's stop here and then do cluster detection.